Hello everyone, this is Wen-Xiang Zhang from University of Science and Technology of China. I'm glad to be here to present our work, Constraint Remeshing using Evolutionary Vertex Optimization. Surface remeshing is a fundamental task in many applications, such as engineering, visualization, simulation, and geometric processing. Thus, it has been widely explored. According to application requirements, some hard constraints are supposed to be met, like bounding approximation error or satisfying the Delaunay constraint. In addition, requirements are considered as optimization objectives, such as reducing mesh complexity and improving angle distribution. Thus, remeshing can be formulated as a constraint optimization problem. However, this problem is rather challenging, and the reasons are twofold. First, it's hard to solve the constraint problem, containing both continuous and discrete degrees of freedom, such as vertex position and mesh connectivity. Second, the most common constraints and objective functions are non-differentiable, such as bounding the two-sided Hausdorff distance, generating a Delaunay mesh, reducing the mesh complexity, and improving angle distribution. To guarantee the hard constraints are satisfied, the trial and error method is developed. It starts from an initialization satisfying the constraints, and then remeshes using local operations that do not violate the constraints by explicit checks. As a consequence, this trial and error method would lead to insufficient optimization of the constraint problem. For example, the error-bounded simplified Delaunay mesh, which is generated by previous work, is still high complexity. Hence, we propose a novel method for high-quality remeshing with hard constraints. The main contribution of our paper is that we propose a simple yet effective method to perform surface remeshing with hard constraints. We successfully apply our method to error-bounded Delaunay mesh simplification and error-bounded angle improvement. Generating a desired mesh can be formulated as solving a constraint optimization problem. The key idea consists of operation decomposition and evolutionary vertex optimization. By decomposing each local operation into topological changes and geometric updates, we observe that the pattern of topological changes is fixed, and the degrees of freedom for optimization consist of vertex position. We use evolutionary vertex optimization to optimize vertex position for non-differentiable objectives and constraints. We convert the constraints into an energy function via the barrier function. Then the constraint optimization problem is formulated into an unconstrained form. When updating a vertex, the variable of the unconstrained problem becomes the position. We design a differential evolution algorithm to minimize it. We briefly introduce the general process of differential evolution. First, it starts from a randomly chosen population that samples the search domain through initialization. Then, it iteratively works through 3 stages, including mutation, crossover, and selection, to involve the population until the termination condition is met. The algorithm terminates when the energy convergence or the maximum number of iterations is reached. New candidate solutions are generated in each iteration. Each candidate is compared to the corresponding one in the current population, and the one that performs better is selected to the next generation. We explain the details as follows. Here, we adopt the DE target to best, 1B form of DE. We optimize only one vertex at a time. When updating a vertex, we represent the case population of DE by a set of vectors. The initial population is obtained by randomly sampling the search domain, which is determined by specific applications. Our strategy is totally sampling on the one-ring faces of the vertex. In the mutation stage, new candidate solutions, donor vectors are generated through this mutation function. The target to best means that the donor vector is chosen to lie on the line defined by the target vector and the best so far vector. One indicates that one vector difference contributes to the differential. Experimentally, we have tested other mutation functions, and the target to best function outperforms others. To enhance the potential diversity of the population, a crossover operation comes into play after generating the donor vector through mutation. It is conducted by exchanging some components of the donor vector with the target vector and building a new vector. Trial vectors are generated through this classical binomial crossover method. At least one element of trial vector is inherited from donor vector. We obtain the population of the next generation by choosing between the trial vector and the target vector according to the value of the objective function. We select the one with a lower objective function value in each iteration. As our problem is a minimization problem, the selected population will never lead to worse performance. We apply our evolutionary vertex optimization method into two applications: error-bounded Delaunay mesh simplification and error-bounded angle improvement. For error-bounded Delaunay mesh simplification, we aim to simplify a surface mesh while constraining the two-sided Hausdorff distance to be bounded and ensuring the output mesh to be a Delaunay mesh, as shown in this figure. We can formulate this problem in this way. The objective function is the number of vertices, and the constraints are error-bounded Hausdorff distance and a Delaunay output mesh. We use the previous method to perform topological operations, including edge split and planar edge flip, to get an initial Delaunay mesh. Since the used operations do not change the shape of the input mesh, the two-sided Hausdorff distance is 0, satisfying the error-bounded constraint. Then we perform the following simplification process to reduce the number of vertices. We only adopt the edge collapse operation to reduce the number of vertices. The position where two endpoints of edge are collapsed is called collapse vertex. We aim to find the collapse vertex position under the Hausdorff distance and the Delaunay mesh conditions. The Delaunay mesh simplification can be reformulated through this barrier function. We run our DE optimization to solve this problem to obtain the collapse vertex position. We use a local method to compute the two-sided Hausdorff distance. If the collapse vertex can be obtained to satisfy the error-bounded constraint and the Delaunay mesh condition, we call the edge a collapsible edge. A demo of the error-bounded Delaunay mesh simplification process is shown here. Our simplification process travels all edges to perform the edge collapse operations until no edge is collapsible. For error-bounded angle improvement, we target eliminating large and small angles as much as possible, while maintaining the mesh to be a manifold mesh and not exceeding the two-sided Hausdorff distance bound and the target vertex count, as shown in this figure. We follow the previous local topological operations, but use a different vertex relocation approach. We first reduce the vertex number to be less than the target vertex count by remeshing, while ensuring the bounded Hausdorff distance. We update vertex position through DE optimization. For the large angle optimization, we optimize the position of the vertex by minimizing the maximum angle of its varying triangles. For the small angle optimization, we only need to change the objective function to be the minimum angle among neighbor triangles of the vertex to be optimized. We test our method in different cases to show its efficiency and robustness. We run our algorithms on a dataset containing 1,606 models. For error-bounded Delaunay mesh simplification, we set the Hausdorff distance bound as 0.1%. Our method successfully constructs Delaunay meshes satisfying the error-bounded constraints for our models. We show the results of 6 complex models. As demonstrated, sharp features are preserved with sufficiently small Hausdorff distance bounds. For error-bounded angle improvement, we set the Hausdorff distance bound as 0.2% and the specified number of vertices as 8,000. Our method succeeds in improving both small and large angles while meeting the hard constraints for all models. We show the distribution of the resulting quality metrics. 6 examples from the dataset are shown here. We first compare the vertex relocation methods in error-bounded Delaunay mesh simplification. The second column updates vertex position by minimizing the quadratic errors under the Delaunay conditions. The third column collapses an edge to one of its endpoints. The fourth column is the random sampling on the one-ring faces of the collapse edge. The fifth column is another derivative-free optimization method called directional direct search, which iteratively generates a finite set of points by adding direction terms to the current point and identifies the best candidate point. We can generate far fewer vertices than the competitors. Our DE optimization is able to effectively reduce the hot-off distance, thereby leading to more opportunities to perform simplification under the error-bounded constraints. Moreover, we compare our method with the hierarchy sampling strategies, which iteratively samples the objective function on a regular grid, identifies the best candidate symbol, and refines the grid in its vicinity. We achieve a better trade-off between mesh quality and efficiency. For comparison, we use the same vertex number strategy, which first runs our algorithm with different hot-off distance bounds, then run the other methods by specifying the same vertex number of vertices as our resulting vertex number, and finally compare the hot-off distances. In the case of the same resulting vertex count, our resulting hot-off distance is much smaller than theirs. We compare our method with a previous method on our dataset. For the same vertex strategy, we set the hot-off distance bound as 0.1% for our algorithm. Through these comparisons, our method is significantly superior to theirs. For error-bounded angle improvement, we first compare our method with a previous method. Using the example provided by the authors, our resulting number of vertices is constrained to be smaller than theirs, and the two-sided hot-off distance is bounded to be smaller than 0.2%. For our algorithm, the angle distributions are similar, but their results violate the error-bounded constraint. To ensure the two-sided hot-off distance is bounded for the above previous method, we modify their method by using explicit checks to reject local operations that violate the error-bounded constraints. However, this method usually leads to poor results. We compare our method with their modified method over our dataset using the same target number of vertices and the hot-off distance bound. The result indicates that our method outperforms theirs. Explicitly checking whether the error-bounded constraint is violated leads to an early entrapment, thereby resulting in insufficient removal of the small and large angles. We present a novel algorithm to remesh triangle meshes with hard constraints. Due to the use of a novel evolutionary vertex optimization technique, our method is suitable for non-different objectives and constraints, such as minimizing the two-sided hot-off distance. We successfully apply our method to two applications: error-bounded Delaunay mesh simplification and error-bounded angle improvement. We have demonstrated the effectiveness and practicability of our method on large datasets. There are two main limitations to our method. First, due to the computing of two-sided hot-off distance, it is not suitable for real-time applications. Second, although our angle improvement algorithm can remove most of the small and large angles, we cannot guarantee that the final angles are always in the specified range for arbitrary models. The reasons are twofold. First, when constraining the resulting number of vertices to be smaller than a specified number, the degree of freedom is so limited that it cannot adequately improve the angles. Second, locked angles, such as angles between sharp features, cannot be changed due to the hot-off distance bounded constraint, thereby preventing all angles from being optimized into the specified interval. The paper and code can be found on this website. That's all. Thank you.